Murushala Devi.
We are Team 7 and we are presenting paper critique for Why Should I Trust You? Explaining the prediction of any classifier paper by Marco, Carlos and Samir. So what this paper is about? So I would like to ask you a question. How many fingers are these?
3.
3. Okay. How did you decide it?
By looking at it.
Yeah, you counted it.
Yeah, I can.
Yeah. So if I create a machine learning model which takes input as an image for my hand and it returns the output of it, how many fingers are there? So how would it decide? If it is a complex model, we might not know how internally it decides. So it's basically a black box. I don't know what if it is looking at my watch, my hand, background of mine to interpret it. So this paper tries to show how we can trust the model, how we can trust the black box. We don't understand it, we don't see it. So this machine learning model, I don't know, it's black box. So how internal works we don't know. So that's how it decides. So this paper make us trust how the model is working. So that's the objective of paper, that we also we have accuracy, we have true positive, true negative, all that metrics to compare a model, but to trust the model, if it is giving the right answer or not, we have this paper. Before it, there has been plenty of works related to this, how we can trust the models. So there was the models are not transparent enough. So what the earlier we used to do is, if we select the transparent model, they are very weak, they are not very strong. The strong and complex models are not very transparent. So that's how the gap was previously, and to make it approximate the values and the accuracy. The real world data does not have the training data, the sample size. If sample size is way higher for the student's grade, the people in this class has higher grades than compared to students who are not in this class. That doesn't mean that it is representing the correct values. When real world data it will see the shift, the model will not be able to predict the outcome accurately. So that was the gap and the previously how people tried to solve it. And what this paper present as a solution is a LIME. What is LIME? It's a local, interpretable, model agnostic explanation. So what it does, as I told you earlier, if I create a model of picture of this, so the output would be basically it will give 3, so I would think, oh, it's accurate. But if I release it into the real world, if the model was looking at the background, this will not accurately predict someone. If it has a white background, so it is predicting 3. But someone with yellow background providing 3 fingers, it might look at the background, not the fingers. Then that might be a wrong prediction. So LIME will do what it will distort the inputs, and it will give it to the model again, and that's how it will try to predict. So the changes in input, how it is showing up in the output, would be the main objective of LIME, and it doesn't provide the completely so this went from this neuron to that neuron, but it provides the approximation that how the black box is thinking. So here are the steps that, for example, the words and image has been provided earlier of a cat's image. So in the second term, if the model's accuracy is high, we want to show it to the world. But before showing it to the world and let them test, we will test that if we distort the data, if half of the cat is gray or black, how it would respond. So the query would go back into the model as a black box, and it will give us the prediction. So it will approximately give us the idea that why why it selected cat earlier and why it is not selecting cat now. And there is update. This is for the individual. The earlier limit was for individual practice, individual prediction. So there is a step above SP limit, submodular pick limit. So what it does, instead of looking for all, if a model has 10,000 inputs, we are not going to check all 10,000 of it individually. That might cost us more constraint and time. So to save resources and to save our time as well, what SP limit would do is pick 100 different kind of inputs that it believes that, oh, this cat is standing, this cat is sitting. If there is 10,000 images of cats and dogs, it will show us 100 examples that based on these different images, it is selecting that particular answer, that particular prediction. That would help us to see if it is covering most of the scenario, if it is looking at the right sample. For the example I gave you earlier of 3 fingers, so if I only receive photos with white background, I have to doubt the input data set, that not because it is counting 3 fingers, it might be looking at the whatever fingers are folded. So the similarities we can see in the short term. So out of that 10,000, we can look at 100 data points and we can decide if our model is doing accurately or not. So I will pass on to Emiliano.
Okay, so we're gonna look a little bit at the mathematical formula for lime. It's a pretty fairly simple equation. There's 3 main components. We'll go over those in a bit. But generally, what does the mathematical function try to do? Basically, what they're trying to do is, imagine a complex model. We're using the English example of, like, let's say we're trying to predict an image, with like 3 or 4 fingers. We could have a deep learning model that's going to be very complex. It could have like so many, like hundreds of dimensions. It could be very complex. It's basically like a black box. So what we're trying to do is, like Divish was explaining, we're trying to select a sample and trying to explain the model around that sample with a way simpler, more interpretable model that we can, visualize, that we can interpret. So that's the whole thing that the equation is trying to do. We're trying to grab our very complex model, then we're going to try to fit a very simple, more interpretable, most of the times like linear model. There's, let's say, 3 main components. The first component is G, which is going to be the interpretable explanation model. It's basically the model that we are trying to create. We are also going to have F, which is the original black box model. So you can see how we are subtracting them. Basically, what we're going to try to do is optimize the loss, that between that like difference of models. We also have a third element, which is going to be the penalty that we're going to add for complex models. So again, I'm going to recap a little bit. We have the model that we are trying to model, the original model, which is a black box. We have a way simpler model that we are trying to approximate. And so we want them to be close. But at the same time, we also have a penalty for how complex the model is. We're trying to find a balance between having something very accurate, but we also want it simple, because if we just approximate a complex model with another complex model, then what's the whole point, So we're trying to balance complexity with also interpretability. We're gonna go to the slide. There you go. So I'm going to talk a little bit about the experimental setup. How is it that they actually did it? What was some of the experiments that they actually tried to be able to prove that these methods, lime and SP lime, work? A key point of this method is it's a generic framework that works throughout like different models. It's not just fixed to a very specific type of model. So they try with many different data sets, many different types of models, and different tasks. They use, for example, sentiment analysis. That's a great example that they tried. They did books, they did DVDs, they did some news groups. I'm going to go into some examples more in detail a bit later, but they showed it like across different data sets. They also applied to different models. There's some like more simple models and then more complex models that are like, again, like black boxes. They did logistic regression, they did decision trees, random forests, they did support vector machines. Again, just to show that it's one of the strong points of this paper. it's a technique that we can apply to many different models. It's a model agnostic. So like I said, they showed it across the board. Same thing with the task they did. The faithfulness of the explanations, basically like how good are the explanations, the ability to assess the prediction trust. Another very important point is, it's not just being us certain that like that's the right model, that's the correct answer, but how are we gonna convey that to a doctor, you know, to somebody that's in a position of power that taking decisions. We have to be able to like explain it to them, and then so we're assessing how faithful the predictions are, how are we being able to like trust the model, how the users actually trust the model. So again, we're gonna go into more detail a little bit later. I'm gonna give a very concrete example of an experiment that they did. Basically, they analyzed a lot of emails, a lot of online group chats, like a lot of posts online, to try to predict if somebody is either a Christian or an atheist. Basically, like they don't believe in God. And they found a model that was 94%, accurate. So I would ask you, would you guys put your money on a model that's 94% accurate? Like I would do it, because like almost 9 out of 10 times I'm gonna be right, I'm gonna get my money. But then what if I tell you that with Lime, they discovered basically that this model, it was using basically like some small like cheating. Basically it was, I have the words here. They were finding that based on the words like posting, host, like RE, from like the emails, those little artifacts, they were using them to cheat. So in reality, they weren't actually predicting if somebody believed in God or not. They found some like shortcuts to be able to predict this. So what is the problem here? In the real life, in a real life scenario, when I'm gonna give it a complete new text, it's actually gonna be a very low accuracy, because again, it's not predicting anything useful, it's just using shortcuts. Once they did, can you go by? Once they applied Lime, again, this technique of like changing a little bit of the words here and there to be able to understand like what is actually that it's using to predict. Once they were able to understand, okay, the model is actually cheating, it's not like predicting if somebody believes in God or not, like it's just using some shortcuts, like some specific words. Then they were able to modify the model, they were able to clean the data set, they were able to fix that, and then the model was actually predicting like accurately. This is a more visual example, another image classification result. It's sometimes a little bit hard, to like actually understand what's going on. So this is a great example because it's something that we can visualize. They had this other example when they were predicting a husky, a dog, versus a wolf. So they had again the model like very high prediction rate, very high accuracy, and they were checking with Lime, how it was actually working, and then they figured out that if you see, this is the image that you provide to the model, this is what it's actually using to predict if it was a wolf or if it was a husky. They found that wolves most of the time were found in the snow, so the model was cheating. It was not actually looking at the wolf or the dog and predicting, it was just looking at the snow and saying, hey, there's snow in the image, it's probably a wolf, because wolves are mostly found on the snow. If it was a husky, then it's probably, So we can see how clearly models tend to cheat. And if they're a black box, of course, in a situation that's more important, when we're treating cancer patients, when we're dealing with like actual life, we need to be able to understand how the models are thinking, how the models are taking the decisions. So again, this is a great example of how we actually apply Lime to try to understand it.
Okay, we're going to look at the conclusion and the contributions, like the summary of what the paper achieved. You see that Lime can explain predictions from any AI model or classifier, not just the simple ones, but by fitting into a local that is interpretable model around any specific predictions. One of the contributions is that it uses the local simple model to make sense of complex decisions. There's a complex model, it breaks it down, it makes it simple for us to be able to get, that makes sensible decisions from it. Another thing is the SP line. It helps us to evaluate the whole model with just a few examples. Instead of explaining one prediction, it picks diverse representative set of instances for a user to evaluate the whole model behavior. And the explanation helps users to trust whether the model is a good model and also to distrust the bad ones. You know, users can trust reliable classifiers and then detect the ones that has flaw, the one that is unworthy. Just like the snow and the animal image we have in the previous slide that is shared with us. We can decide that, oh, we can't trust this. This is not doing the good job. It detects the flaws in it. And also, one of the contributions is that Lime and SP Lime have proved that the old tools have real and practical values, like we could see from the previous explanation. And we'll go to the strength of the paper. These are the analysis of what this paper what it does very well. You see that Lime works with any classifier. That's one of its advantage, like the SVM, the random forest. We see the neural network. It's not limited to just one type. It is huge. It's a huge practical advantage to it. Another is the interpretability. It produces explanations that humans, those are the back ends, humans can read and understand. It translates complex decisions into human readable terms. It is easy to understand. Another is that it backs claim with actual user studies. It's not just about the theoretical metrics or the claims, but the real user studies. This strengthens its credibility. It also detects the hidden problems in the training data, just like they mentioned earlier. It exposes dataset leakages and the spurious correlations, e.g., for example, a model learning from irrelevant signals, just like the snow that we had previously. It was picking what wasn't relevant. And then it is widely used today. It's a sign that it genuinely solves a real problem. It has a lasting influence and it solves real problems that we can see and that can stand the test of time. Now let's go to its weaknesses. These are the areas that Lime falls short.